Welcome. Today we're tackling Leetcode problem 2503, maximum number of points from grid queries. It's marked as hard, and it involves grid traversal with an interesting twist related to query limits. Here's the problem statement. We're given a grid of numbers and a list of queries. Each query is a value k. For each query, we start at the top left cell, in row 0. We can move up, down, left or right. We get 1 point the first time we visit a cell, but only if the query value k is strictly greater than the value of the cell we are currently in. If k is less than or equal to the current cell's value, we stop moving from that path. We want to find the maximum number of points we can get for each query. We can revisit cells, but only get points on the first visit. Let's look at the first example. The grid has values like 1, 2, 3, etc. The queries are 5, 6, and 2. For the query k equals 5, we start at 0, 0, which has value 1. Since 5 greater than 1, we get a point. From here, we can move to 0, 1 with value 2. 5 greater than 2, get point. 1, 0 with value 2. 5 greater than 2, get point. We continue exploring. We can reach cells 0, 0, 0, 1, 1, 0, 2, 0, 2, 1. All these have values less than 5. We cannot enter cells with values 5 or 7. The total number of unique cells visited with values less than 5 is 5. For k equals 6, we can visit all cells with values less than 6. These are 0, 0 equals 1, 0, 1 equals 2, 0, 2 equals 3, 1, 0 equals 2, 1, 1 equals 5, 2, 0 equals 3, 2, 1 equals 5, 2, 2 equals 1. That's 8 cells. We cannot visit 1, 2, which has value 7. For k equals 2, we start at 0 equals 1. Since 2 greater than 1, we get 1 point. Can we move anywhere else? 2, 0, 1, value is 2. 2 is not strictly greater than 2, so we stop. 2, 1, 0, value is 2. Again, 2 is not strictly greater than 2, stop. So we only get 1 point. The output is 5, 8, 1. Let's note the constraints. The grid dimensions m and n can be up to 1,000, and the total number of cells, mn, is up to 100,000. The values in the grid and the query limits can be up to 1 million. The number of queries k can be up to 100,000. These constraints suggest that a solution that runs a separate BFS or DFS for each query might be too slow. If each search explores most of the grid, OMN, the total time could be OKMN, which could be up to 10 to the power of 5, 10 to the power of 5 equals 10 to the power of 10 operations, definitely too slow. We need something more efficient. The key insight here comes from observing the relationship between queries. If a query queue allows us to visit a certain set of cells starting from 0, 0, any larger query queue where q greater than q will allow us to visit at least those same cells, potentially more. This suggests we don't need to recompute everything for each query. We can leverage this by processing queries. Instead of answering queries in the order they arrive, we sort them by their limit value. We also consider the grid cells sorted by their values. As we process queries in increasing order of limits, we can incrementally add cells to a structure that tracks connectivity. The union find data structure is perfect for this. It efficiently manages sets of connected elements and allows us to merge sets and query the size of a set. So, here's the plan. First, we pair each query with its original index, so we can put the results back in the right order later. Then we sort these query pairs based on their limit value. Second, we create a list of all cells from the grid, storing their value and coordinates, like value, row, column. We sort this list based on the cell values. Third, we initialize a union find structure. This structure will have mn elements, one for each cell. We also need an array to store the size or number of points associated with each component, initially 0 or 1 depending on implementation. We also need an answer array for the results, and a way to track which grid cells we've already processed and added to the DSU, like a Boolean visited grid. Fourth, we use a two-pointer approach. One pointer iterates through the sorted queries, and the other iterates through the sorted grid cells. For the current query, limit, original_index, we advance the cell pointer, adding all cells with value less than limit to our DSU structure. When adding a cell, we mark it visited, initialize its component size to 1, and then check its 4 neighbors. If a neighbor is valid and has already been visited, meaning its value was also less than the current limit, we perform a union operation in the DSU to merge the components of the current cell and the neighbor. During the union, we correctly update the total size of the merged component. After adding all relevant cells for the current query limit, we check if the starting cell 00 is accessible, i.e., if grid 00 is less than the current limit. If it is, we use the DSU's find operation to get the root of the component containing 0, 0, and retrieve the size of that component. This size is the answer for the current query, which we store in the answer array at the original underscore index. If 0, 0 isn't accessible, the answer is 0. Finally, after processing all queries, we return the completed answer array. Let's quickly review the union find data structure, also known as Disjoint Set Union or DSU. It's designed to keep track of elements partitioned into a number of disjoint, non-overlapping sets. The main operations are find, which determines which set an element belongs to by finding the set's representative or root, often using path compression to flatten the structure for future lookups, and union, which merges two sets together, often using union by rank or size to keep the trees shallow. For our problem, we need to customize it slightly. We'll add an array, let's call it points, where points stores the total number of grid cells, which correspond to points, belonging to the component whose root is I. When we initialize the DSU for n elements, where n is m times n, each element starts in its own set, parent equals I, and points is initially 0. When we add a cell RC, corresponding to index IDX equals Rn plus C, because its value is less than the query limit, we find its root equals find IDX and increment points by 1. Then, when we perform a union IJ operation, after finding the roots root underscore I and root underscore J, if they are different, we merge them. Let's say we make root underscore I the parent of root underscore J. We update the parent array, parent root underscore J equals root underscore I. Crucially, we also update the points count. Points, root underscore I, becomes points, I, plus points, I underscore J. The points from root underscore J's component are now part of root underscore I's component. Here's the complete Python code. We define the DSU class as discussed. In the maxPoints method, we get dimensions m, n, and k. We create sorted underscore queries by pairing limits with original indices and sorting by limit. We create the cells list containing I or R, 10k, tuples, and sorted by value. We initialize the DSU for mn elements, the answer array, and the visited grid. We use cell underscore IDX to track our position in the sorted cells list. We iterate through the sorted underscore queries. Inside the loop, the while loop advances cell underscore IDX, processing cells whose value is less than the current limit. Inside the while loop, we get the cell's info val, bamperum prec. We calculate its 1D index cell, underscore ID. Crucially, we check if not visited before processing. This ensures we only add each cell and its point once. If it's a new cell, mark it visited, find its root, and increment the points for that root's component. DSU, points plus, equals 1. Then, we check its 4 neighbors. If a neighbor is within bounds and already visited, meaning it was also added because its value was less than the current limit, we perform a union operation between the current cell and the neighbor. The union method handles merging components and updating points. After the while loop finishes for the current query, all cells with values less than limit have been added and connected in the DSU. We then check if the starting cell grid has a value less than the limit. If it does, it means we could start the process. Since the while loop ensures all cells less than limit, including 00 if applicable, are processed and marked visited, we can confidently find the root of cell 0, root 00 equals DSU.find 0, and retrieve the total points in its component. We store this in the answer array at the correct original underscore index. If grid 00 is not less than limit, we can't even start, so the answer remains 0. Finally, we return the answer array. Let's analyze the complexity. For time complexity, sorting the mn grid cells takes O(mn log mn time. Sorting the k queries takes OK log k time. The main loop involves iterating through the sorted queries, k iterations, and the sorted cells, mn iterations total across all queries. Inside the loop, for each cell addition, we do a constant number of neighbor checks, Each check involves DSU operations, find, potentially union. With path compression and union by rank/size optimizations, though not explicitly shown in the simplified union, the principle applies. These operations take amortized time O, alpha mn, where alpha is the inverse Ackermann function, which grows incredibly slowly and is practically constant for all conceivable input sizes. So the total time for DSU operations is roughly O, mn plus k, alpha mn, which is very close to linear in mn plus k. The dominant terms are the sorting steps. Therefore, the overall time complexity is O, mn, log, mn, plus k log k. For space complexity, we store the sorted cells list, which takes O, mn space. The sorted queries list takes OK space. The DSU structure requires arrays, parent and points, each of size O, mn. The visited grid takes O, mn space. The answer array takes OK space. So the total space complexity is O, mn plus k. And that's how you solve the maximum number of points from grid queries problem using offline processing and union find. This approach efficiently handles the constraints by avoiding redundant computations. If you found this explanation helpful, please like the video, subscribe for more Leetcode solutions, and leave a comment with any questions or suggestions for future problems you'd like to see covered. Also, you can help me continue making these videos by donating at buymeaboba.com. The link is in the description below. Thanks for watching.